Thank you, Anna-san. Good afternoon. I would like to talk about the early environment of the Earth, particularly focusing on the time period called Archean. So first of all, what is Archean? Archean is a time period from 4 billion to 2.5 billion years ago, when the Earth's surface is and totally covered by water and with no continent, on only small volcanic islands. And higher heat flux of this age, we believe that volcanic activity is higher than today, so the hydrothermal activity is also higher than today's. But the surface temperature is very controversial. Many people believe this period is hotter than today, but not so sure. And the biosphere is dominated by prokaryote, and because the onset of oxygenic photosynthesis and atmosphere is believed to have been free from molecular oxygen. Instead, the geology textbook said, CO2 is a main component of the atmosphere, along with maybe nitrogen. But the quantitative estimate of the CO2 level is still a matter of debate. How much CO2 is there? We don't know yet. And of course, lot of the other gases, species in the atmosphere is largely unknown. So I'd like to focus on the three questions in my talk today. And how much, first one is how much CO2 in the Archean atmosphere. And more broadly speaking, how and what control the redox state of the Archean atmosphere. And chemistry of atmosphere is very important also for climate through the greenhouse effect. So finally, I talk about the link between the atmospheric chemistry and climate. So I like this symposium poster, blind man touching and see the shape of elephant. So my talk is I am one of these blind person. So and to understand. Trying to understand the atmospheric chemistry of the past Earth. And my favorite tool is stable sulfur isotopes. This is very tricky because we don't know direct sample of the Archean atmosphere. That's why indirectly we are trying to estimate or study the chemistry of the past atmosphere. And the sulfur has 4 stable isotopes, sulfur 32, 33, 34, and 36. And the abundance of these isotopes are, for example, 34 is 4.21% in the textbook. But in reality, this abundance has changed. Sometimes this number is not 4.21, but sometimes 4.23 or something, a little bit changed through physical process, chemical process, or biological process. And in that case, the enrichment factor of sulfur 33s compared to the most abundant 32s is about half of that of 34s. This is a golden rule. It's based on the quantum mechanics, but we call this a mass-dependent relationship. But few exceptionally, the photochemistry, a few photochemistry in the gas phase reaction do not obey this rule. So that's why the deviation from this mass-dependent relationship, we define the deviation from this relationship as a cap delta value. The non-zero cap delta value is a sign. Something happening in the atmosphere chemistry, and the signal can be brought into the sediment. And about more than 15 years ago, the Farquhar first found this sort of isotopic anomaly from the geologic samples, particularly older than 2.3 billion years ago. So this isotopic anomaly is known to be produced by the photodissociation reaction of SO2, very, very exceptional, and preserved in sediment if atmosphere is anoxic, free from oxygen, because the sulfur entering into the atmosphere as a form of SO2, and anomaly yielding reaction is removal of this oxygen and making SO. This is responsible to make this isotopic anomaly. But if this reducing form of sulfur and remaining SO2 are further oxidized into sulfate, the very oxidizing form of sulfur, and the 33 rich compound deposited with a positive anomaly, and the oxidizing species acquire negative anomaly. So this happen under the reducing atmosphere. But once the atmosphere is oxidizing, no reducing species are formed. That's the sulfur entering into the atmosphere is totally oxidized into sulfate and deposited. So that's why after the rise of oxygen, this sulfur isotopic anomaly disappeared from the sedimentary rock record. And modeling studies show that to preserve this isotopic anomaly, the atmospheric oxygen level should be less than 1 ppm. Okay, this is the basics. So that's why the presence of this anomaly means the very, very reducing anoxic conditions. But we don't know yet why this valuation changed through time. So in this 10 years, many people, including our groups, study which process is most important for controlling the isotopic ratio of the aerosol species, which are deposited and finally preserved in the sedimentary rock record. So in the laboratory, we studied each step of reaction and determine the fractionation factors of 4 stable isotopes. And so this is like the shape of elephant is like, this is very complex. Not that this is a very simplified view, but in reality, the atmospheric chemistry is very complex. But in short, the key step is only 2. One is a photodissociation of SO2, and the other one is a photoexcitation process of, again, SO2. So we use the experimentally determined fractionation factor and put into the chemical reaction network model and predict the isotopic anomaly preserved in the sediment as a function of the chemistry of the atmosphere. Yeah. And we changed the surrounding chemistry of the atmosphere, and this pathways changed due to the different chemical composition of atmosphere. And when we change the PCO2 level and calculates the this is the isotopic degree of the isotopic anomaly, and we found that even without no oxygen, high CO2 level is not preferable to preserve the isotopic anomaly. Again, even without oxygen, molecular oxygen, the too much CO2 is very, very oxidizing. So the CO2, pure CO2 atmosphere is oxidizing atmosphere. So not only PO2 level, but also the PCO2 level can constrain by this isotopic anomaly studies. So this estimated level is less than 0.1 bar. This is lower than the PCO2 CO2 level, solving the faint young sum problem. This figure is already shown by Werner van Roch in the first days of this symposium. And I don't add much things, but this yellow band shows the stability region of liquid water on the surface of the Earth in response to the increase of the solar luminosity. So the lower band means the freeze of the water, and this is vaporized threshold. So less than 0.1 bar. Our estimate is that this is the maximum, but the other lines of evidence, mainly from the absence of the iron carbonate minerals from different ages of weathering profile, means much lower predicted estimate a more lower PCO2 level. So it's consistent with several other independent studies. And this said that the CO2 is not enough to keep the Earth warm enough to solving the faint young sun problem. So that's why we need the more greenhouse gases. And trace gases like methane or ammonium or somewhere else may be added. Not only CO2, but also the other trace greenhouse gases may be responsible for keep the Earth warm enough to stabilize the water, liquid water. So the next thing is from the other isotopic anomaly, and we can see lots more about the atmospheric chemistry. If we look at another isotopic anomaly for sulfur 36s, this is the most least abundant species among the 4 species. And this x-axis shows the isotopic anomaly of 33s, and the y-axis shows the isotopic anomaly for sulfur 36s. And the 3 anomalies are mutually correlated. And these red dots are all the sedimentary Archean geologic record. And this shape must be produced by the primary photochemical reaction, because the anomaly yielding reaction is very, very exceptional. But if you look at carefully, this magnitude and slope or ratio between the 3 anomalies changed through time. So that could be some signal from the past atmosphere. But we cannot read why this magnitude and the slope are changed through time. So that's why we need more experiment. And previous researchers photolyzed SO2 in the laboratory, and succeeded to produce the isotopic anomaly, both sulfur 33s and 36s. 0 is a no anomaly. So the result is very successful to produce very, very exceptional isotopic anomaly. But the problem is that this data point is consistent with the geological record. So if this trend is produced by the mixing between the sulfur derived from atmosphere and the other sulfurs in magmatic or biological, not derived from atmosphere, is 0, always 0. So the atmospheric component should be somewhere around here, but no data point is on this line. Okay, that's a big problem. So why this experiment cannot reproduce a geologically observed trend? We think the two key reasons. One is the partial pressure of SO2. The previous experiment is too high compared to the real world. And another thing, important thing, is the redox states. And the pure SO2 is very, very oxidizing condition. Photolysis of SO2 is always produce excess oxygen. So the pure SO2, the presence of SO2 itself create a very, very, very oxidizing condition. That is far different from the presumed reducing atmosphere of the Archean period. So that's why to scavenge the excess oxygen, we put the carbon monoxide in the chamber and do the same sort of experiment by using solar like UV source. And also we reduce the partial pressure of SO2. This is 1,000 Pascal, 100 Pascal, 10 Pascal, and 1 Pascal. And then we can see this trend. And some data points are, okay, we can reproduce the geological trend. This is because the presence of SO2 itself changed the spectrum of the UV within the chamber. So that we call the self-shielding effect. So the different wavelength region cause the different isotopic fractionations. So the changing the UV spectrum by the presence of SO2 itself is very, very significant. Too significant. So this column shows the isotopic ratio of 34, 33, and 36 as a function of the total SO2 column densities in a log scale. And the previous experiment, the too high, compared to the modern level, So even after the huge, intense volcanic eruption, like Mount Pinatubo or in Japan, Miyakejima Island, that's a gigantic release of SO2 is happening in 1991. But still, only 2 orders of magnitude higher than the normal modern level. Okay, so in the actual realistic range of the PSO2, we can see the reasonable range of the reproducible range of the isotopic anomaly. And in other words, the partial pressure of SO2 can change the magnitude of the isotopic anomaly. So this isotopic anomaly can be used to monitor the PSO2 level, sorry, or can be used to monitor the volcanic activity. So, but the problem is not solved yet completely because this slope is not like this. So something additional fractionation is overlapped. So we argue that this trend, this yellow data is by using the solar-like UV spectrum. In fact, we use the xenon lamp. But this is the spectrum of the xenon lamp that is similar to the solar UV flux spectrum. But if we change the spectrum like this, and this trend is shifted. So we can see some additional things that's happening. The difference between the two spectrum is the wavelength regions. And SO2 is not only photodissociated but also photoexcited in the longer wavelength regions from about 250 nanometers. So different process can make different isotopic fractionations. And the solar UV can proceed both photolysis or photodissociation and photoexcitation, both. But if we use this one, only photolysis occurred. To test this scenario, we cut this wavelength region by using the optical filter and test the photoexcitation effect. And yes, we can see the huge isotopic anomalies. And this is far different from the geologically observed trend, but photoexcitation process produced this vector of the isotopic fractionation. So we should think about the the mixing of two processes. One is photodissociation, and one is photoexcitation, and create different manner of isotopic fractionations. But the key thing is a Redox state or amount of the reducing gas in the atmosphere. Okay, SO2 is photolyzed into SO, and some SO2 is photoexcited in the longer wavelength regions. But this excited state of SO2 has an isotopic anomaly, but easily quenched back into ground state of SO2. So this isotopic anomaly is not transferred into the final product, usually. But if the atmosphere containing reducing gas species in our experiment, that is CO, but in fact, the reducing agent remove the one oxygen from the excited state of SO2 and transfer into SO and mix together, and these two signals are mixed and transported into, and finally preserved in the sediment. So that's why the slope of these two isotopic anomalies can change by the amount of reducing gases. If the atmosphere is reducing, and this slope is shallow, but its atmosphere is oxidizing, and this slope is steep. And the magnitude is controlled by the PCO2 level. That it may be related to the volcanic activity. So now we have a model, and we use this experimental data and model how the product and the remaining SO2 is changed in this diagram as a function of SO2 partial pressure and CO partial pressures. And we conclude that about 1% of carbon monoxide is present in the atmosphere. We can reproduce this slope. Or methane or hydrogen also as a candidate. So as I mentioned earlier, the Archean atmosphere is not a pure CO2, of course, and more reducing than previously thought, and possibly including 1% amount of CO or methane or hydrogen. Okay. So the question is, this sort of high CO atmosphere is possible or not? Short answer is yes. And because the CO2 is always photolyzed into CO and oxygen, but the back reaction, CO plus O into CO2, this is spin-forward reaction, so very, very, very slow. The only sink reaction of CO is a reaction between OH radical, a hydroxyl radical, that is formed by the photolysis of water. So that's why at least the upper part of the atmosphere, CO2 atmosphere, the carbon monoxide level is increasing. But if the atmosphere contain or the system contain the sufficient amount of the reducing agent, CO can be sometimes accumulated in the atmosphere. And this one-dimensional model shows that if the molecular hydrogen level is high, or CO level can be exceeded against the CO. So the key question is where the reducing agent came from, the hydrogen, or I think the most likely abundant reducing agent is iron, 2+. Ferrous iron is always supplied by the hydrothermal activity and the vent. So I not talk about the process between atmosphere and ocean and vent, but in terms of the budget, the iron flux is large enough to scavenging this OH, that is oxidizing CO into CO2. So as a result, if the iron is not scavenging OH, iron oxide is precipitated, and in fact, we can see a lot of vanilla iron formation in the Archean period. So now let's go back to this slide. We can monitor reducing gas amount and the volcanic activity through these two things of the isotopic anomaly. And if our model is correct, the variation or magnitude of this scatter means the volcanic activity. The large variation means the higher volcanic activity. Smaller variation means the lower volcanic activity. And if we look at the slope between the two anomalies, the shallow slope means a reducing condition, and the steep slope means the oxidizing condition. So we can at least separate the Archean period before great oxidation event, at least into 3 parts. And atmosphere can be fluctuated, reducing, oxidizing, reducing, like this. Okay, and these two time periods correspond to the higher volcanic activity at that time. At the same time, the atmosphere is reducing. And this is consistent with the previous geological record. This is figure shows the occurrence age distribution of the vanilla iron formation that may implies the higher hydrothermal flux of iron into the ocean. Yes, yes, abundant, as less and abundant. And also the archetype volcanism, the age population of granite is very strong. So the late Archean period after 2.75 billion years ago, it's a high volcanic activity and also hydrothermal activity, and providing a reducing agent and atmosphere time into reducing. So back to this slide, I like to say, the water log reaction, the hydrothermal reaction is very, very, very important, not only for ocean, but also atmosphere. So I like to say, this figure is the misleading to consider the how the chemistry of atmosphere modern can change. In reality, we have to see like this. Earth is a rocky planet, so the ocean volume is only 0.02%. It's easily buffered by rock through the water log reaction. That is weathering hydrothermal reaction. And also atmosphere is only 0.0004%. Okay, to me it's easy to change by the reaction between the rocks. So we have to consider about the link between lithosphere and atmosphere and ocean. And also this might be linked with the climate. And this period is I didn't explain this blue lines, the potential glaciation event. This is Pongola, this is Botswana, and this is from southern India. We found recently. Okay, CO2 is not the major component to control the climate or temperature. And the other reducing gases is important, you know. The CO2 capture the window region of the IR emission that escaped into space, but equal amount of energy can absorb only 1 ppm of the methane, or the other gas like OCS can be produced if under the CO-rich atmosphere. So we have to think about more trace gas, but trace gas is not trivial to consider the temperature of the atom, the earliers. So I should stop here. So thanks for listening.
So we are happy to accept your questions or comments.
Yeah, the at 2.7, the increased volcanism, is that, could you interpret that as the increased SO2 volcanism and not just, I mean, could it be the change in the gases that volcanoes are putting up rather than a volcanometry in general?
That's very interesting point. But I think the archetype volcanism, the sub-area volcanism tend to have much more SO2 compared to H2S, because the pressure, the lower pressure, the SO2 level is compared to SO2 H2S ratio of the volcanic gas is increased.
Increased in sub-aerial volcanism.
Yes, low pressure. So sub-aerial volcanism, like island arc volcanism, is responsible for that. So yeah, if we look at the seafloor volcanism, we can see different pictures. So that's an interesting point, I think.
Just a question again about the volcanism. Is there a reason you chose not to think about large igneous province volcanism? So those fissures back then, or at least if you predict how high they go, they put a lot of stratospheric SO2 into the exosphere.
Could be, yeah. But we don't know much about that. So, arc volcanism emit much more SO2 compared to, basalt type. I guess, but
not compared to Laki, right? So the example we have recently is Laki.
Laki eruption. Yeah. So, yeah, large igneous province also increased at the late Archean time, but this type of comparison is still it's vague. So, yeah, I like to compare with that, age distribution large igneous province too. But yeah, if you have the the best data set, so please.
Similar question, but I'm a little confused that how reduce the volcanic gas, because this picture is very clear. That my question is how reduce the volcanic gas, and if you don't have a reaction with the hydrothermal activities, and then could you make a reduced atmosphere?
Assuming the amount of Redox state that's buffered by KFM on average, and then the volcanic gas should be dominated by H2O and then CO2. But addition of CO2 is not, I think it's trivial, because if the 0.1 bar of CO2 is already available in the atmosphere. So, but the interaction between lithosphere and hydrosphere or atmosphere is two types. One is direct addition of gases by volcanic activity. This is high temperature process. But I'd like to mention more lower temperature interaction. That is hydrothermal circulation, and also weathering of continent or seafloor. That should be taken into account. That is my what I'm trying to say. Yeah.
Maybe one more. As if Earth didn't have any ocean, surface water, you couldn't have any hydrothermal activities, and then, but you have
You mean no
like-
water, but
like
fluid.
Mars, and if you don't have any
I see.
water on the surface, and then volcanic activities could not produce the reduced atmosphere, right?
I only said in terms of budget, but I don't argue that the mechanism. So yeah, that's. I think it's interesting, and water is a very good medium to facilitate the reaction, I think. So yeah, I can't imagine so far, but yeah, it's an interesting question.
Can I ask you a naive question? So can you extrapolate some part of Hadean atmosphere, or Hadean environment from your results?
Mm-hmm. That's very difficult, but it depends on the model. So how fast the Werner showed their first day, and how fast the the CO2 level is buffered by the the several processes, and we can provide the one boundary conditions. So I think it depends on the model. So if we don't have not much geological samples, so geochemist doesn't say anything directly. Yeah.
We still have 5 more minutes, so yes.
Hey, Yuichiro. Also, possibly a naive question, but I was wondering if, with the amount of SO2 that you think is going into the atmosphere, if that would connect to these big sulfate deposits that are found at around 3.4 billion years ago, these North Pole barite things that...
Yes, I think so. For at least some deposit. Yeah, because our why it doesn't change. But well, anyway, to produce a large isotopic anomaly, that needs the very dense optical thickness of SO2. But the lifetime SO2 is very short, several years, not million years. So that's why I think that anomaly producing a process a very a short phenomena. Like after the volcanic eruption, for example. Yeah. So several sulfate deposit may be related to that kind of volcanic event. Yeah, that's likely possibility, I think. And records can be local.
Yeah, you have a picture of banded iron formation. You have the letters Fe on top of it. You say it equals reducing atmosphere. When there is a reducing atmosphere, what is it that's varying that's producing the stripes in the banded iron formation? Is this subaqueous volcanism or something, or what is it?
Yeah, that's a huge argument. There is a huge
Do you have a
argument.
view on this
But
argument?
yeah, it could be the part of the in the periodic emission of the vent that can create valve-like structure.
So
That is one possibility.
Okay, intermittent emission of Fe2 from hydrothermal vents.
That is one possibility.
Okay.
And then somebody says this is, annual, like a daily or yearly cycle, but it's still controversial. But it's possible to deflect the, periodic input, hydrothermal input.
And the other people who disagree with that say.
Yeah, there are long, debate. Yeah, we can talk about that.
I'm sorry, we still have 5 more minutes.
What? Sorry. Yeah.
I have a question, if possible. Hi. I very much enjoyed your presentation. Thank you. And
Thank you.
with some colleagues, we published some work that suggests that air pressure at around 2.7 was less than modern, right? And I was wondering if that would magnify the effect of a sulfur injection into the atmosphere, and would that be reflected in the signal?
If it is nitrogen, it's not magnified. That story is the same. Yeah, but if CO2 levels on 1 bar or 10 bar, that's a totally different story. So because the CO2 is shielding the this wavelength region responsible for the SO2 photolysis and excitation. So it's highly relevant if total pressure is decided by CO2. But if total pressure changed by N2 denitrogen, that's invisible for me. I can't
good.
see elephant.
That's good. Thank you.
Any other naive questions?
Hi, great talk. Just want to ask you, you commented that the most important input to early Earth's atmosphere might have been the input flux of ferrous iron. Why? Do you think that the outgassing of reducing gases, those fluxes should be smaller than ferrous iron? Thank you.
That's simply because of the the estimated flux and likely possibility, but compared to which one?
Yeah, the
or
so you mentioned that the flux
hydrogen
is like 10 to
from
the 11th
volcano?
moles per year. So
Uh-huh.
if I just convert it into
oh, that is a present day flux from
Oh,
the
okay.
modern atoms.
So you can increase-
modern seafloor.
okay.
Yeah, they could be higher than that. Yeah.
Is that okay? Okay, so let's move to let's thank the speaker again.